Hello, I'm Aurora Sicilia-Aguilar from the University of Dundee, and I'm going to talk to you about reading between the lines, which is the work that we do in Dundee using time-resolved high-resolution spectroscopy and photometry to map the innermost structures around young stars, including accretion, the inner disk, and winds that are associated to these structures. So if we are talking about disks, the first thing that we need to notice is that because of the temperature and chemistry structure, one wavelength doesn't fit all. So if we are interested in knowing what happens in the innermost disk region, or in the accretion columns, or in the disk winds, things that are happening between a few stellar radii to a few AU, then we need to go to a quite energetic signal. So if we want to do spectroscopy, we need to think in terms of optical spectroscopy. Now the issue with that is that we won't be able to get a resolved image, so then we need to be inventive and try to use other methods to map these kind of timescales. And the other method is time, so we can use time and velocity to map space and learn about these structures. So the way this works is essentially for every spatial scale we can think about, if we have a signal traveling at a certain velocity, this is going to result in changes on a given time scale. Now the good thing is that for tiny spatial scales, we are also going to have short time scales. So if we are interested in knowing what happens in the accretion columns or in structures up to fraction of AU, depending on how this signal is traveling, if it is traveling at the speed of light, it's going to change in matters of seconds to minutes. If it is something like a Keplerian rotation or sound wave, then it's going to need between hours to days. So this is very easy to track if you are using time-resolved photometry or spectroscopy. If you're interested in longer timescales like planetary orbits, then your timescales are going to be of the order of years. But what you also need to think about is that we have now a wonderful collection of very good data. So photometry for several decades and spectroscopy, high resolution, for 20 years. So you can also trace pretty big timescales and spatial scales with all this data. And this is what I'm going to talk to you about, using two objects as examples so that you can see the power of this method and what we can do if we continue going beyond in this direction. So the first one of my objects is J1604, which is an object that has two disks. So it was first known to have a face-on disk from observations such as these scatter light images that you see here. So you see a very nice big face-on disk, about 60 AUs in radius, but you also see that the disk seems to have a couple of dents. And then because these dents are changing from day to day, they can be related to structures that are located at 60 AUs, so they have to be shadows from something that is happening inside. So in this way, we managed to trace a picture that you can see here in the cartoon of the disk, where you have two disks face on, and then an inner disk that is nearly 90 degrees inclination with respect to that. And is casting the shadows, and is also able to explain other things such as the object being a dipper, and also the rotational velocity and the rotational period that we observe for the object. But this is not the only thing that you can do for this object. So this object was also observed with Kepler, and if you have a look at the Kepler light curve, it looks a bit like a messy sort of thing because it's changing all the time. It doesn't seem to be periodic, but it's actually quasi-periodic, and it's telling us about unstable accretion. And also because this inner disk is nearly 90 degrees inclined, what we are seeing producing all these eclipses are actually the footprints of our accretion columns where it is attached to the disk. Now, if you have a look at the accretion rate, you will realize that the accretion rate, although not too high, is high enough to remove and recycle all the material that we see in the eclipses in intervals of 10 or 20 days. So when you observe the same accretion column again after 5 days, which is the rotational period, you are actually seeing a very different material. So you can track the structure of this inner disk just by using photometry, and it's not only the structure of these accretion columns and their footprints what you can do, but for instance, if you look at the colors and the dust extinction, you will also realize that deep eclipses have a different dust properties than shallow eclipses. So this inner disk has also different particle sizes. This is for very short timescales, but this object has been observed for a long time, spectroscopically and photometrically. So if you look at the spectra, you see that they look different and the accretion rate is changing. So you get cases where the object was accreting, like this green one has a very nice redshifted absorption. It's typical of objects that are seeing etch on. But some other times you have nearly no accretion. If you look at the photometry, you see also all the time there are eclipses, more or less, happening consistently over the past 10 years, but sometimes you see periods where there are no eclipses, although you would expect them. The other thing that people have seen about this object is that the Weiss and Spitzer data on the inner disk are not consistent. So this object sometimes has a near-infrared axis and sometimes it doesn't. And now if we put together the longer timescale, we see that actually when the accretion rate is low or non-detectable, this is also the same time when we have no eclipses. And it's also the same time when we have no near-infrared axis. So this inner disk is having major changes in timescales of 2 or 4 years, which are probably related to something that is living inside the big gap of the inner disk. And that's to be investigated in the future. Another source that we have been looking at is ZCMa. So this is a very different type of object because it's a pretty massive binary object. So the companion is the one that is more famous because it's an F-Orionis object, although it has been quiescent for the last about 20 years. And the main source is actually a Helbig B star that has accretion bursts. The nice thing about accretion burst in any type of object is that because a star becomes a lot more luminous, the inner disk also becomes hotter over a bigger range. So then we can, with our optical spectra, zoom in or rather out in regions that will not be visible otherwise. So we can learn a lot about the structure in the inner disk. So ZCMa has a lot of lines and has a lot of neutral lines and ionized lines. So the neutral lines, such as the iron 1 lines, they have this type of profile with 2 peaks. So these are typical of disk profiles, and they trace material between a fraction of AU to several AUs. You have a lot of iron lines with different strengths and different transition probabilities, and you can also see that they look different in profile. So in general, the lines that are weaker, they are tracing material that is deeper in the disk, and the other lines, they trace material in the outer layers. So also with emission lines, we can trace the vertical structure of the disk. We can also compare the red and the blue side, and we see, for instance, that is slightly asymmetric. And we also see that it's more asymmetric in the outer layers, which makes sense. For comparison, you can see here what the line profile looks like in quiescence. So this is the red one here, which is a very narrow one, probably originated in a spot around the stellar surface. If you now look at the other lines, which are the ionized lines, you see the profile are totally different because we are tracing material that has a very different temperature and density. So in this case, the profiles of the lines are tracing accretion and a very hot and complex non-axisymmetric wind. So the orange profile is a profile that you see in quiescent, and the blue one is the profile that you see in outburst. That is a lot more variable than in quiescent and has all these peaks. These peaks correspond to different types of wind, different wind components, and because we see the wind components changing from day to day, we know that it's a non-axisymmetric wind that is rotating with the star. We can pick up disk wind and stellar winds, and surprisingly this is very similar to what we observe also in low mass XOR outbursts. So it looks like there is a continuum of properties between stars that have accretion bursts, no matter what their mass is. The mass of ZCMa is probably about 6 to 8 solar masses, so it's a really big one, but it's not so different in properties compared to other objects like X-Lupi, that is less than 1 solar mass. It's not only that you can get information about the velocity structure, you can also get information about the temperature and the density structure. So because we have so many iron lines, although the iron atom is very complicated, we can find lines that are coming from the same upper level. And in this case, we don't really care about how the levels have been populated, but we can use the line ratios observed in lines that are coming from the same level to place constraints on the temperature and the density. And this is what I'm showing here in this figure. Using different iron lines, we can also trace the material that is going at different velocities and then constrain what is the temperature structure and the density structure around the object. So the main limitation when we are doing this emission line analysis is that it's very complicated. So modern spectroscopy is able to reveal a lot of lines with a lot of information around most of the young stars. But how to get there, how to use this data to obtain results in a reasonable time, and that is where the work of my postdoc, Justin Campbell-White, kicks in. He's developing a Python-based code that we are calling star melt, and that is doing all this line extraction and analysis. So we are feeding template spectra that can come from any spectroscope that you have, as long as it's high enough resolution. We are using these spectra to identify the emission lines that we have. We can match them to known lines to derive the atomic properties. We can then use the line properties to fit them and to obtain time and velocity structure during periodogram analysis, or we can also look at the line profiles and the ratios between lines to obtain information on the densities and temperatures. So mixing together the time resolution that tells us about the location of the source and the density and temperature resolution, we can get a very good idea of what is happening around the object. So you can here see a view of what the star melt code looks like. It's a full Python code running as a Jupyter notebook, and it will be made public at the end of the project, but we are also open for collaboration from any time starting now. And also, although we have been applying this to young objects mostly, there is no reason why it should not be extended to other sources that have also emission lines to fit them and analyze in a temporal and velocity manner as you like it. So with this, I'm coming to the end of my talk, and my final messages are that emission lines are an extremely powerful method to map the inner structure of young stars, their accretion, their wings, the different wing components, the structure on the disk, how they are evolving with time, and to get an idea of what is happening there with unprecedented resolution. They can also provide information on the physical properties, density, temperature, and it doesn't need to be applied just to young stars. It could be also applied to other sort of objects. We are also developing this star melt code, so for more information about that, I really suggest you to go and have a look at the talk by Justin Campbell-White, because he will explain then how you can use this code to study time-resolved observations of any kind of object that has emission lines. And what you also need to remember is that we are gathering a lot of very good quality observations in time. So the more data we get in the archive, the best understanding we can derive about these objects. So this can only get better in time, and we will have a star melt code that will be very good to learn the most we can do from this data. So thank you very much for listening. And if you have any questions, please don't hesitate to contact me. Thank you very much, and bye-bye.